Everybody. So we continue with our ECT star. Today we have Babis Anastasiou. Babis he did his PhD in elementary particle physics, theoretical particle physics at the University of Durham in the United Kingdom. And then he took his PhD in 2001. Then he has held postdoctoral fellowships at very prestigious places like SLAC, ETH, Zurich, and CERN. And since 2007, he was appointed as an assistant professor at ETH Zurich, where he was promoted to associate professor and then to full professor since 2012. So he's working on perturbative quantum chromodynamics with an emphasis on applications to collider physics phenomenology, and he's one of the experts in precision, in doing calculations for the precision Higgs physics program at the LHC. So today he's going to talk about some new techniques. So I let him present us what he has done recently.
Okay, thank you very much for having me here today in your seminar. And it's a good opportunity for me to tell you about perturbative physics, but from a point of view that utilizes a lot the non-perturbative information that exists into Feynman diagrams. So I will talk about how to create two-loop finite amplitudes that in principle can be calculated directly in d equals 4 dimensions without the need of regularization. This is a work that I'm doing together with George Sterman, Ryan Heidel, Chu Yang, and Mao Zeng. With the exception of George Sterman, all the others are at ETH in Zurich. So I will talk about a class of events that they happen at colliders, and they are relatively easy with respect to what you as specialty deal with at the ECT in Trento. They are easy because they refer to very well separated final states like jets and events that they involve large momentum transfers. So when we are looking at this type of processes, then the non-perturbative effects, they take a rather simple and beautiful form, the very well-known collinear factorization form that was developed by Colin, Soper, and Selman, where practically we can separate non-perturbative information from some hard scattering cross-section, and the latter we can calculate it in perturbation theory. By calculating more and more diagrams, we can go to higher orders as well. So in the last decades, we have become better in climbing up this ladder of perturbative calculations and to calculate and simulate events like this with higher and higher precision. What does one gain when we do that? Well, let me just flash a few recent results that they happened in the last couple of years. And they are at next to leading order in perturbative QCD. You see in these plots the two processes. One is Drell-Yan production, the inclusive cross-section, as a function of the invariant mass of the lepton pair, which is created via a virtual photon. And you see here the ratio of the cross-section at a specific order with respect to the final order that we have. This is NQ below. So 1 corresponds to the NQ below cross-section at a certain scale, which is the scale Q of the invariant mass of the lepton pair. And of course, you notice here that the reduction of the scale uncertainty is very large, and you can really talk about very precise physics at the highest order. What I want to point out is that these calculations, they don't happen easily. So the next leading order happened a few years after the development of QCD as a theory. And the next connection in order only happened in the 90s. And the next order, NQ below, has only been added now, so many decades afterwards. This means that in order to go from one perturbative order to the other, we have to learn a lot. We have to understand how to, the mathematically and computationally, the nature of Feynman diagrams that they get involved in that. The calculations are not only at the exclusive level, the calculations become more and more differential. At NLO, everything is differential. At NNLO, it is well understood how to make cross-section calculations differential. The formalism is there, but the ingredients are not always there for all processes. Nevertheless, we have many NNLO differential calculations. And now, also at NQ below, we see the first differential calculations, for example, the Higgs repeated distribution. So this is where we are, and you would argue that this is already a great shape. We have precision for high value processes, which ranges from a few percent to 15%, let's say. And this is great for the comparison with the LHC data because the experiments are exactly at this level of precision right now. However, we would like to go further. And this is motivated due to the high luminosity LHC physics program. So we would need to calculate 2-to-1 processes, perhaps at N for LO. This is not for phenomenology mostly, but it is in order to understand the convergence pattern, to make sure that what we believe it is precise at NQ below, it is indeed precise. So a lot of work has been started already in this direction. For 2-to-2 processes, the data motivates that we advance our precision from 10 to 15% at NNLO down to a few percent at NQ below. And for 2-to-3 processes, that they are very important signals for Higgs physics or very important background for Higgs physics or potentially new other physics signatures, we need to move from NLO to NNLO. So this is a very ambitious program. And our techniques are great, but we need to make them better. We will not have any good chances to tackle these new frontier calculations in 5-10 years from now if we don't invent new ways to do our calculations. What I will argue here today is that we can advance our techniques if we dig deeper at the essentials of perturbative QCD and use information that is not used so much. One such information comes from the non-perturbative contributions to Feynman diagrams and a good understanding on how to separate them out from what is truly the hard scattering contributions. For that, in the last few years, we have seen a lot of progress in consolidating factorization theorems. So now we know, and this has been proven in full glory in momentum space in a paper by Yao Ma and also in a paper by Matthew Schwartz with different techniques. It is consolidated that for an arbitrary amplitude, when the final states are well separated, the amplitude can be written as a product of 3 amplitude factors. So it would be a product of an amplitude for a hard scattering, another factor for soft exchanges, and another factor with collinear splittings. And actually, it's not one factor, it's as many as the final states or an initial states in your process. What is nice about this factorization is that it is universal. It applies to every process as long as the scattering is at wide angles, as long as you have large energy transfers. So this is nice, but paradoxically, we don't use this information when we calculate amplitudes. What we do is we calculate the full amplitude, and only at the end, we recognize the jet and the soft factors, and we separate out the hard cross-section. So we don't have direct way to calculate what is relevant for the physics that we want to measure, the hard scattering process. And this is something that we thought that with my collaborators that perhaps we can do better in the future, and maybe it will help us to do less calculations and to go faster to the computer to do the work for us rather than us calculating many functions, polylogarithms, expansions in dimensional regularization, and so on and so forth. So I would like to describe what are planning to do in this direction and what we have achieved so far. So let me take again this factorization theorem and say a few words more on how we hope that it can work at the end. So what we are doing right now is that we take an amplitude, we dice it into pieces, and we do a lot of algebra to express it in terms of a few integrals, which we will call master integrals. Then we develop very sophisticated techniques that they take these master integrals and expand them around d equals 4 dimensions. And this gives rise to complicated functions which are of polylogarithmic nature, and they depend on the momenta. And at the end, we go to numbers. This is a very well-tested chain, and it has become very powerful. So we do get 99% of the results that we have right now in perturbative QCD. And the idea that we have is that we drop all of the mathematics and computational techniques that they do this reduction to master integrals and expression of them in terms of polylogarithms. And instead, we take the amplitude, we separate out the soft and the jet functions, and that we know that they are universal, and we have computed them at very high orders already. And what we have here is the numerical piece that it corresponds to hard scattering. It's the amplitude integrand divided by the soft and the jet factors. In principle, this should be free of singularities. And if so, then we should be able to integrate it out. This expression here is an all orders expression. When you expand it, so all of these factors, the amplitude and the soft and the jet factors, they depend on the QCD strong coupling. When you expand it out, what you create is that this gives you subtractions to the original amplitude at each order in perturbation theory, which render the singularities finite. So at leading order, you get from this ratio that the remainder, this ratio is giving you just the 3 amplitude. At 1 order, you get a 1 loop amplitude minus some universal jet and soft factors times the leading order 3 amplitude, and so on. So what this factorization theorem points to is that at each order, you can take the amplitude, subtract some universal factors times previous orders, and you should be getting something finite. So this should be a recursive process that we hope to be able to do. So you may ask, why are you not just doing it as it is? It looks straightforward. And I have a simple visualization of the answer to this question. And later on, I will try to explain in more details what the problems are. So let's, by the way, this is Boris. And since in the last few months, I was doing a lot of homeschooling for him, and I could not really do physics, I was developing these pictures with him. So that's what I'm presenting here. Nevertheless, they were very good for me to understand what I was trying to do. So let's suppose you have an amplitude, and the divergent pieces are these Tetris pieces here. Okay, there are singularities. What the factorization theorem tells us is that we should be able to separate from the amplitude the divergent pieces. So we should be able to subtract them away. The other thing that the factorization theorem say is that these divergent pieces are actually nice. You can put them together in a nice way, and you will get things that you recognize from previous order amplitudes. So this is the idea. You take an amplitude, remove the divergences, and at the end, all of these organize itself in a very nice way at all orders in perturbation theory. So what you would like to do is to turn it around, and you will say, let me take this piece from here, which is nice, and I know it, and universal, and add it directly or subtract it directly from the amplitude. Then I'm guaranteed to get a nice hard function. I'm guaranteed to get a nice remainder of the integrand, which is finite. But let's see what we've done in order to get this nice geometry at the end. We took one of the divergent pieces, this one, and we rotated. So we made some transformation. What does this mean in practice? Well, if you try now to put this piece back to your subtracted integrand, it doesn't really match the singular structure anymore. When you rotated it, then you don't have a point-by-point cancellation of the singularity. Therefore, this is something, this nice result is something that definitely holds when you care about the value of the surfaces that they add up together to the original amplitude, but point by point you lost the cancellation of divergences, so you lost locality here. In order to make a Monte Carlo integration of a finite remainder, then point by point you should make sure that you have a singularity. So all of these nice proofs of factorization theorems, here and there, they use this type of non-local arguments. And it's not immediate how to it's not immediate or clear how to use the result of the factorization theorems as local subtractions at the integrand, canceling all the singularities. What we try to do in this work is to go in the proofs of the factorization theorems and find alternative arguments that they do not destroy locality. Let me give you an example of how we would solve this toy problem here. So let's take the amplitude and make a second copy of it. So we rotate the full amplitude as well. When you have these two copies, then you can subtract from each of the copies the divergences. But then without any rotations, without any transformations, the divergent pieces organize themselves into nice blocks. We did the proof of factorization here for twice the value of the amplitude. And the integrands of the amplitude are rotated. They are transformed by a change of variables, let's say. But it doesn't matter. What it is important is that for this combination, the blocks that we subtracted, they are nice and they fit exactly the singularity. So this piece here will go up here. This piece here is going to go down here. And the blue pieces are going to fit the singularities of, sorry, I pointed wrong, but the pieces are going to fit without making any rotations at the end.
So, Babis, can I ask a question?
Sure.
So when you say you take 2 times the amplitude, of course, in the end, you need one amplitude, but somehow you take, let's say, half of it, and you take some change of variables so that you do some process, I don't know, of symmetrization or whatever. So in this way, you make local cancellations by...
Right. So at the end, what you're interested in is the surface, is the volume of your integral. And if you calculate twice the volume, it doesn't matter. You remember it and you divide at the end. But what you achieve here is that the integrand of it plus the integrand of this, they combine nicely.
I see.
And when you subtract the divergences, they are already in the form of, let's say, lower order amplitudes. And this I will try to show it a little bit better with physics examples and Feynman diagrams at the end. But yes, you have to you have to make the work twice apparently. But making it twice, it's easier, or it's nicer than trying to do it for only one copy of the amplitude. So this is a new way, alternative way, and we are not sure it's going to work at all orders. So we have tried it in some example. Let me give you one of the, let's say, analogs of how this looks like. And Dionysis may relate to that because he was a big basketball fan and playing a lot of basketball when he was young. Dionysus, you may remember that at some point, in order to learn how to shoot, they were telling us to use just one hand. And these things like this, they ask you to play basketball with only one hand and try to do score and win. And of course, we are very much learning about it, but you know, basketball is very inspiring because we have seen people that they can do amazing things with just one hand. And I believe that we can do a similar thing. We can really prove factorization theorems, which are very difficult things to do, without really using all of the material or all of the tools that they were used originally. So we started with a process and not full QCD. We just started with QED. And the process is Z plus E minus to many photons. The aim was to see if we can make subtractions for all of these amplitudes, irrespectively of the number of photons in the final state. So what I will talk to you about is, it will be on this process, but I will try to see whether some things can be generalized or not. So I will discuss the origin of the singularities in these multi-loop integrals, and then I will discuss how they can be removed according to factorization theorems. And then explicitly, I will show how this works at one loop, and then how it works at two loops. And then I will give you some prospects in the future, whether at the end we can take this technique into a practical machinery for calculations. So let's start by looking at the singularities. I think in your audience, I don't need to say much, but let me just remind a few things for the sake of having some reference for the later parts of the talk. So the singularities in the amplitude, they come from the denominators, and they come from the denominators of propagators. Here, I'm sorry, I'm missing an omega squared, but what you have is poles from the denominators, and each propagator contributes 2 poles. Now, these poles are very close to the integration path. So in principle, they can lead to singularities. However, if you are able to deform the contour of integration away from these poles, then there is no singularity. And many of these poles can be deformed away. The situations that they cannot be deformed away are 2. One is when a soft particle, a massless particle is soft. Then the poles align themselves on top of each other, and then you are not able to deform the contour away from them without hitting one of them. So this is a true in infinity, and we have to subtract it away. So this really gives a non-perturbative contribution to the amplitude. The other situation with massless particles in your process is when you have collinear emissions. Then one pole from one propagator aligns with a second pole from a different propagator, the particle that it is collinear to the original one. And again, you have a situation that you cannot deform the contour. One can go through the Landau equations and do a more, let's say, systematic study, and this has happened in the past for the proof of factorization theorems from Sterman and Collins and Soper, for example. And what you see is that this is all. If your amplitude corresponds to wide angle scattering, if you are only interested in well-separated final states, then you only have soft and collinear singularities. But then how do we deal with them? How are they subtracted away from the amplitude to separate the hard contribution from the soft and the jet functions? We need a power counting criteria. Again, this all exists in the proofs of factorization. So what is the idea? The singularities, they lie within a surface or a manifold in your integration domain. Every type of singularity corresponds to a different surface. I have just visualized one of them, but here, let's say this is one singularity. What you can do in order to see whether there is a divergence or not from this singular surface is to parameterize locally on the surface and around it your integration variables, so that some variables are parallel to the surface and some are perpendicular to the surface. Then you can scale the perpendicular variables by something small and examine how fast the integrand combined with the measure becomes divergent as you drive the parameter to 0. So, for example, the parameterization of a soft singularity is particularly simple. You say that all components should be of order delta. The soft singularity resides in one point in the integration domain when the momentum is exactly 0. So you scale it, you also scale the measure, and then you examine the integrand and you see whether you get a degree of divergence which is positive or negative. The collinear singularities are a little bit more complicated, so they are extended, but you can parameterize the components, some of them to lie on the plane of the singularity and the others away, and then you can scale them again in a way so that the denominators are remaining on shell, and you can again see whether there is a collinear or soft singularity. So we have this power counting criterion in order to be able to assess whether a singular surface is indeed singular enough to give a divergence when you integrate the amplitude. Once we have identified a singular surface, we can remove it. We can remove the singularity. Suppose you have only one singular surface where the contour of integration is getting pinched and you really need to remove it. What you can do is you can make an approximation of the integrand on that singular surface and then remove it from the amplitude. It's a simple subtraction. This combination now is free of the singularity. But of course, you cannot throw away what you took out. You have to integrate it again somewhere separately. And this separation is what it really gives rise at the end to a hard, soft, and jet functions. The situation of one singular surface is particularly simple, but reality is more complicated. You have more types of singularities. And the singular surfaces, they touch each other, they overlap, they are quite entangled. So how do you deal with a situation that you have to subtract more than one type of singularities? Again, the factorization theorems give us a very practical solution on how to do that, which is actually quite robust. What they do is to order the volume of the singular regions according to their size. For example, a soft singularity, as I said before, it corresponds to 1 point, so it has no volume, 0 volume. A collinear singularity has a bigger volume because you can find certain directions in your integration domain that this singularity occurs. So the volume of a collinear singularity is bigger than the volume of a soft singularity in practice. This volume criterion can become very precise, and in the latest proof of factorization theorems, this is made very, very precise. But let's be more intuitive for the purposes of the presentations here. Then you start by subtracting the singularities which correspond to the smaller volumes. This means that you subtract soft singularities before collinear singularities. And once you removed one volume, you go to the next one and next one. And this recursive process makes sure that you don't have double counting. You don't make a subtraction at a later point that will reintroduce a singularity that you thought you subtracted before. So this ordering is guaranteeing this. Well, when I first learned about it, I was a bit skeptical how this worked, because I have seen in the literature many attempts that these criteria are kind of rediscovered, but without explicit references to this nested subtraction technique that I just described. So with George Sterman, we tried it out in specific two-loop examples, and we made a paper on this. Why can one be very skeptical? Well, because the entanglement of singularities can be really very threatening. So here, I show you a representation of the entanglement of singularities for the double massless box. So this is a graph here, and it has seven denominators. What you see here is that you start for a situation where the denominators are completely off-shell, so there is no singularities in this region. So this is the true hard region. And then you take collinear or soft limits, and then you see which of the denominators remain off-shell. This is, let's say, a poor man's way to estimate the size of the volumes for each of the singularities. If more, let's say, propagators become on-shell, then the volume of the singularity diminishes. And what we see is that you can arrive to the same type of configurations with many ways. In practice, this means that your singularities overlap in multiple ways. So it is remarkable that the technique can separate the singularities without really double counting. And what we did is we faithfully adopted what the factorization theorems told us. We have to remove first double soft singularities, then soft collinears, then double collinears, then soft, and then collinear. And at two loops, this seems to work very nicely. I'm not going to bother you with many examples here. We did the planar box, the cross box, and things that they are considered to be complicated, and they seem to work. So this is what the factorization theorem tells us, that you can subtract the singularities in a very nice ways. And what they say more is that once you subtracted them, they organize themselves to something nice. This organization into something nice does not happen for random terms in an amplitude, but it happens for full amplitudes. So let me show you this in one example. The example is the one loop, and later on the two loop amplitude for E plus E minus to a large number of photons, as many as you like. And I will do this in QED in Feynman gauge. The choice of gauge is nice. If you change the gauge, you can change the nature of collinear singularities, for example. Axial gauges have a different behavior diagrammatically. But the Feynman gauge is the one that we like to use in modern high-order perturbative calculations. So it gives a simple structure in the denominators. So how do we subtract the infrared divergences for these amplitudes? I have here a presentation of the amplitude. It consists of 4 types of diagrams. Here, in the first type, you have diagrams where you get loop corrections, but in the inside of the graph, where all denominators are off-cell. So these, they may have UV singularities, but they don't have any soft or collinear singularities because of really being correction to what one would call the hard function. A collinear singularity can appear in this type of graphs when you have an incoming particle which splits into 2 particles, and these can become collinear. And there are many of these graphs. So this collinear photon can end up anywhere in the hard part, in the off-cell part of the amplitude. You get it for one leg, you also get it for the second leg. And finally, you can have graphs where a photon connects the initial states, and they can have singularities that they are collinear to one particle, collinear to the second incoming particle, but also on top a soft singularity. So these are these types of graphs that you find, and as you see, they have a variety of singularities that I just discussed. According to what I told you before, I should subtract away first the soft singularity. So in order to do that, I need to find an approximation of the amplitude in the soft limit when this particle here has almost 0 momentum. What then happens here? If this exchange photon is soft, it does not really bother the incoming particle. So the incoming particle is on cell, and it remains on cell here. When another photon is emitted from the final state, then the other propagator following the incoming on-cell propagator becomes off-cell. So all of these propagators here become off-cell. The incoming ones next to the exchange photon remain on-cell. So a good approximation of the amplitude in this region is to take this part of the graph as it is and take the rest of it without any flow of the loop momentum in it. So practically take the momentum equals the loop momentum equals 0 limit to what is off-cell propagators in the rest of the graphs. When you do that, you have an amplitude which is at 3 level as part of multiplying a factor. These multiplications, we will keep it in spin space. One can really do it to the end and subtract the true amplitude out. But we thought it's a little bit easier to keep it as it is. So we keep the spin indices open here and here. And in order to simulate the external spinors, we have instead of them some projectors that they do that. So this is a spin sum, but at the end of the day, it can also be written as a true sum of some scalar function times a 3 amplitude. So there we are. This is the expression that we have. This is the one loop amplitude, and the soft limit is the 3 propagators that they remain on cell attached, and the hard propagators in here, they are calculated with zero loop momentum flowing into them, and they are at 3 amplitude. So And this is what you expect from factorization. Now let's go and study the collinear singularities. The graphs that they contribute to the collinear limit, they can be collected in this type of representation. You have the incoming particle, it splits into two particles that they can become collinear, and then these particles join into some hard subdiagram. What one can find out, and I will not be very brief on that, is that if you take the limit in this corner of the graph and you simplify it, then this amounts to essentially replacing the metric. I will do it here. Replacing the metric of the exchange photon with only the longitudinal components. So practically, a very quick way, and that we also know from the factorization of collinear singularities for Parton distribution functions, in order to take the collinear approximation, is to take the exchange photon and make it longitudinal. Then you have the collinear limit of the amplitude. This is a great result because when photons become longitudinal, word identities are at play. So this longitudinal photon will attach itself everywhere else in the graph, except on the propagator that it originated from, because this will be a correction to the external state that we throw away with the LSZ formula. But when this happens and the photon is collinear, then vertices become differences of propagators, and this leads to cancellation. So practically, if you take, let's say in 2-to-2 scattering, this collinear contribution at all permitted places in the graph, then you will have terms applying the word identity that they will cancel each other, and you will be left only with one, which is a correction to the incoming leg. And this is your jet function. This is the factor that goes inside the jet factor of the amplitude. Now, what we have observed is that for a specific choice of parameterizing the collinear singularity, then this factor can be made to look like a soft approximation as well. So practically, the soft factor that I calculated before is having the same collinear limit as the rest of the diagrams. And just to cut the story short, we can make one subtraction for both soft and collinear singularities once we know that they factorize. And this is that. We take the one loop amplitude, we subtract the expression where we have the form factor, the 2-to-1 process, but instead of having just a single photon coming out from here, we put a full 3 amplitude in that. And this combination is at the integrand free of every singularity. Are there questions on this part before I go to 2 loops?
So okay, let me ask something. So where is, you said that in the final state, I think in the beginning you said that in the final state you need very well separated outgoing particles in angles, right?
Yeah.
So I guess this is coming in here in some assumption regarding the momenta that you label like Q1, Q2, which are the outgoing particles, right? So
right.
Presumably you assume that this Q1 and Q2 don't become parallel, or
right. So Q1 and
it's
Q2
kind of
don't become
obvious,
parallel.
right? But I wanted to see that, you know, I get it right.
Yeah, this is very important because if you get in a situation that they become degenerate, parallel, or they correspond to a high energy limit, as you know very well, then what I said before, that the singularities are only soft and collinear, is not correct. you will have additional regions. And then I would need more subtractions. And as you know very well from, let's say, the BFKL equation, then the factorization is not the same. You get a different type of description of non-perturbative physics in there. So
basically, this is mostly some the initial state singularities, right?
No, also the final state has to be separated from the initial state as well. And the initial, right. It is here only initial state because I only have photons in the final state. If I had an electron positron in the final state as well, then I would need to discuss more singularities.
Okay.
But again, of the type soft or collinear, not of other types, not of Glauber regions and things like that. Okay, so now I will go and discuss a couple of things at two loops. Very briefly, I promise to keep myself on time. So, well, we can do that. Here it was kind of effortless. We actually wrote down the amplitude, and we just saw that the soft and collinear singularities cancel out. But let me point something out here. Suppose that instead of L, in one of the diagrams, I had made a shift. Suppose I had called this L plus P1 or something else. I'm allowed to shift momenta in loop integrations without changing the result. Then the cancellation of the word identities would have been spoiled. This is really a partial fractioning identity. If you decide in one of the terms, so if in this term you change L to something else, then you are not going to get cancellations in between these two diagrams. So even here, I had to fix an ambiguity of what do I mean by an one loop amplitude integrand. This ambiguity is more pronounced at two loops. So you have to assign loop labels to all of your diagrams. And we have to do it in such a way so that factorization is respected. So this is, again, something that we have to figure it out. And we have not figured it out for everything, but we have figured it out for the process that I'm discussing here. So let me show you what we are doing. So we take the diagrams, and we call one momentum L and the other K. And then you can say, well, why would you do that? Well, what we do at the end is we symmetrize over these two labels. So we take the amplitude and we exchange L and K. So this is the copy I was discussing before. And then we do something more. Since, as Dionysus pointed out, the singularities are coming from the initial state here, we have a plane that these momenta define, and we reflect the momenta on the transverse direction of the loop momenta on the transverse direction. So this is not just the amplitude, but it is 4 copies of them. We are allowed to do that without changing the integral over these variables, these kernels, these integrands. So let me show you why we do these things. So let's look at a class of graphs that they contribute to a divergence when one of the photons becomes collinear to the incoming leg. The word identity, in order to have factorization, wants that this photon attaches everywhere in the rest of the subgraph. And when you do that, you get the full cancellations. So when you have all of these 4 contributions where the photon attaches everywhere, then you get a correction to the incoming leg. So this is a jet function times and 1 loop subgraph. Let's now look at the second limit, where the photon wants to become collinear to the other leg. You will get mostly other graphs, but one of them will be shared, will be the same. So one graph contributes to both limits. Well, actually, not only one, but also this graph contributes to the same limit. In order to have factorization in this limit, it is important that the momentum k attaches next to the collinear incoming particle everywhere. But here, what you want to call k for the k parallel to P1 limit, here wants to be called L, the other momentum. Unless you symmetrize, you are not going to have a factorization of the singularities. So that's what we are doing. We are symmetrizing in the two labels, and then for most limits, the factorization is immediate. So here is the graph. Sorry, I could have shown that before. So this is one of the problems that we have to solve. And the second problem that I will discuss here is of a different nature. So suppose you have propagator corrections or vertex corrections close to incoming legs. What we show at the one loop level is that when the other momentum becomes collinear, then this propagator here becomes longitudinal. It gets a longitudinal polarization. And this was important in order to make the word identities to work. What happens here is that for loop corrections like this, close to the incoming legs, you don't get longitudinal polarizations. You only get them if you integrate out this propagator or vertex corrections. So when you integrate them out, then this other photon becomes longitudinal in collinear limits. However, this we want to make a local subtraction. So we are not allowed to integrate out a part of it because then we will not know how to integrate out the rest of it. So we don't want to do that, and we have to find an alternative solution. So let me, well, I have to be brief on that. Let me go to the result of this discussion. Well, what we do in order to solve this problem is to take these subgraphs and substitute them with something else. What is this something else? This something else is something that has the same integration volume, so it doesn't change the result for the amplitude value, but in parts of its expression, it is symmetrized over routings of the momenta. So this is not a global symmetrization, but it is really surgical to specific graphs that they spoil, that they give non-longitudinal polarizations to collinear photons. And when we do that, we manage to preserve word identities everywhere for all collinear singularities. So at the end of the day, after this hard work, what we managed to do is to be able to factorize our singularities. And here is how our subtractions look like at two loops. We take the two-loop amplitude, then we take the 2-to-1 amplitude with some complicated vertex, which is full 3 amplitudes, but without any loop momentum dependence, and subtract them away in this term here. These projectors are instead of the external spinors in the kernel. And then we subtract a one loop form factor times the finite part of the one loop amplitude that we computed before. And this does it all. So at the end of the day, we have made manifest factorization at the integrand level. And this is an alternative proof of factorization for this type of processes at 2 loops. The last complication is rather standard, with only a small caveat. We don't only have infrared divergences, we have also ultraviolet divergences, and we have to create counterterms for them that they are local. But this has already been achieved with BPHZ, and we do exactly the same thing here as they were doing there. One complication is that when you make a local counterterm for a graph, then you have an ambiguity. You can write these counterterms in many different ways, and the differences can be only finite parts. However, you have regions where, sorry, I have to be a bit faster and I have a little bit more material. You have regions where you can have a UV divergence together with a collinear divergence. And for this type of graphs, you will be creating counterterms. Now, your counterterms have a chance, and this is what was happening before in the literature, to spoil to spoil word identities. So not only you want the amplitude to satisfy the word identities, but you also want the counterterm diagrams to satisfy the word identities for these mixed UV plus collinear regions. So we made sure that our counterterms respect our word identities, and this was, and we found a good method in order to achieve that. So at the end of the day, the conclusion is that we can do everything local, both infrared and UV, just being a bit careful not to spoil factorization at any of the steps. And we did a numerical check. We computed the degree of divergence in all possible collinear limits, and we found that as delta goes to 0, there is no singularity. The amplitude scales properly. Okay, a very last comment, if I have time. I told you the main part of our work. The question is whether we can turn it into a computational tool. We have an integrand which is free of singularities. Then in principle, you can put it into a Monte Carlo integration and integrate. But in practice, this is not what you can do. You also have to deform the contour of integration a way of poles that they don't give pin singularities. They don't give soft or collinear singularities. So finding an algorithm for doing these deformations is very important. I just want to say that an independent group at ETH found a very great algorithm that does it. And they have already applied it to the one loop amplitudes that I described before. And they can compute, let's say, a 5-point function very, very nicely and easily with a few numerical precision. But what it is also beautiful is that they can calculate 2-loop finite integrals with 1, 2, 3, 4, 5, 6 legs in here with very, very high precision. So now that we are going to be publishing the results that I presented here in this talk of finite integrands for 2-loop amplitudes, we are just looking forward to see if this integration technique, it will be able to compute it, to compute our amplitude remainders at 2-loop. So just to conclude, I presented here the subtraction of infrared and ultraviolet divergences at a local level for a class of QED amplitudes. For us, this is a case study for generic amplitudes in Gates theory. And what we wanted to show is that indeed one can do it locally. You can subtract the singularities and preserve factorization. So you can have very simple counter terms that they cancel the singularities. And this is the first step and a quite important step in being able to do perturbative calculations in exactly d = 4 dimensions. There has been a lot of progress. We are also thinking about QCD, and we are making a lot of progress as well. So more results will be presented in the future, I hope. And there is also a lot of progress in really taking these finite remainders and computing cross-sections fully numerically. I hope that this will allow us to do processes with many final states in an automated way in the future. And simply because we don't really have to go into expressions, into Feynman diagrams and do something on each one of them. We just prepare the integrand, we subtract globally the singularities, and the rest will be integrable. So I hope to be able to tell you something physical in a year or so from now. Thank you very much for hearing me.